So sorry about missing the recording. Forgetting to hit the record button for 15 minutes. But hello, we're back with Math 221B, so just as a quick review for those of you looking sort of going back to sort of watch this lecture again. So we had this one result about sort of a little diamond of field extensions, and so the two things we know about a sort of big field extension encompassing K and K prime that encompasses extensions K and F prime is that the degrees of the smaller field extensions divide the degree of the big extension. That's K. That's the little k and little n divide big N, and that the degree of the big extension is less than or equal to little k times little n, but there's no divisibility guarantees there. Okay, so yeah, and there's the proof, and which if you want to go back and review the proof, you can actually just sort of go look at the slide. And so now we're on to finding the irreducible polynomial of an element over a base field F, capital F. And so we're going to go over, there's sort of two general methods for finding an irreducible polynomial of an element gamma over of a field extension over some base field F. One is, I think this is the method we're about to use, is to keep taking powers of gamma and eventually get a linear dependency. And the reason we, and remember that we know that if gamma is algebraic over F, this must eventually happen. In fact, you have some experience doing this in some other context. Earlier on in the course, you may remember sometimes when you had to find degrees of various find irreducible polynomials, find those kernel elements. Remember, so this must eventually happen if gamma is algebraic over F, and so move this little box here. Yeah. Yeah, so if gamma is algebraic over capital F, this must eventually happen because this is contained in some finite dimensional vector space over capital F. Or another one that works occasionally is you can kind of guess the other you can symmetrize. We'll see some examples of when that happens later, and guess the other roots of what we hope is the irreducible polynomial, and multiply out the linear factors x minus gamma sub I to get what we hope is the irreducible polynomial. That only sort of works in this sort of pretty much only works in special circumstances where we know the symmetries of gamma and its friends. Yeah, that's super vague. Okay, but we'll see some. I believe we'll see. Yeah, we'll see some examples of this when we get to finite fields. Soon enough, and certainly when we get to Galois theory in chapter 16. All right, so we're going to focus mostly on this is the main method that we'll look at today. There we go. Is this thing where we take powers of gamma? So let's do an example of that. He said optimistically. Okay. Right. So here's an example. So let K be Q adjoin alpha. The rationals adjoin alpha, where alpha cubed minus alpha squared minus 1 is equal to 0. Let's see. Oh yeah, I guess we should prove that this is irreducible. That would be helpful. So does anybody see why this is irreducible? Excellent. So Ravi says because there's no zeros in F2. That's right. It's irreducible because it's irreducible over F2. Yeah. So as you saw, this is one of the great methods of proving that something's irreducible is that you sort of assuming that it has as integer coefficients is that you reduce it mod something and then show that it's irreducible there. Yes, and this is, so yeah, so x cubed minus x squared, x cubed plus x squared plus 1 and x cubed plus x plus 1 are the two irreducibles of degree 3 over f2. I think that was a homework thing, maybe? Anyway, yeah, so, but you know what? Ravi said it much more efficiently. This is x squared, x cubed minus x squared minus 1 is irreducible because it has no zeros in f2. So we're going to find the irreducible for gamma equals 1 plus alpha over q. All right, so let's see how this goes. Well, let's see. So we know that alpha, he said, we know that alpha has degree 3. Alpha has degree 3 over q. So so q of alpha has dimension 3 over q. So you can't. So if we look at 1 gamma, if you look at the set containing 1 and gamma squared and gamma cubed, that is linearly dependent, and so at least at that point we'll get something. We'll get an irreducible polynomial for gamma, and in fact, well, I guess well, let's see how that goes. Okay, so I'm going to switch to handwriting. Always a dangerous thing here. So 1 is 1. Well, 1 is 1. Okay, I think you'll all agree with me there. Gamma equals 1 plus alpha. Gamma squared is equal to 1 plus 2 alpha plus alpha squared. I immediately see this is going to be a problem because it's going to require me to do linear algebra in 4 variables in front of a camera, basically. So please bear with me or help me out here. My apologies for having thought of this in the first place. Gamma cubed is equal to 1 plus 3. I said 1, yeah, 1 plus alpha, good. Okay, 3 alpha plus 3 alpha squared plus alpha cubed. Okay, so far? So I'm just multiplied all that out. So now, this relation here, the important thing here is that I think this is why I chose this, is that this relation here, that alpha cubed minus alpha squared minus 1 is equal to 0, tells you that alpha cubed is equal to alpha squared plus 1. And so we can replace this alpha cubed with alpha squared plus 1, and so we get 2 plus 3 alpha plus 4 alpha squared. And so let me say that as we'll see, especially in the section on finite fields, I should just do this with my finger. It really doesn't work well with the mouse. Okay, so as we'll see in the in this section on finite fields, so when you have the irreducible of some element alpha, the way you compute with alpha is you sort of take the top term and rewrite it in terms of, you can rewrite one of these kinds of relations as saying that this top term can be rewritten in terms of lower degree terms by putting everything else on the other side. And so yeah, so this fact that alpha cubed is equal to alpha squared plus 1 is what allows us to compute here. So yeah, so again, that was the key point. See if I can change colors here. That was the key point that we get from here to here, because alpha cubed equals alpha squared plus 1. So does that make sense to everybody? I'm looking on the chat here. All right, so so we could actually, gosh, I guess we could actually set this up as like a an honest to God linear algebra problem. You know, this is, in fact, for those of you who are teaching Math 18A, this is a back solution for three equations and three unknowns. Okay, but let me instead do this by guessing, which is actually, this is more or less equivalent to back solving. So change color back here. So we see that so I'm going to sort of guess here. So in order to match that, in order to match this coefficient of alpha squared, I'm going to guess that, well, what you have to have is something like 4 gamma squared. So 4 gamma squared is equal to 4 alpha squared plus 4, oops, not 4, but 8. But 8 alpha plus 4. And so we're off from what we want here by 3 alpha. So what we want a little bit closer is 4 gamma squared minus 5 gamma is equal to 4 alpha squared. And we subtract 5 from both. Let's see. So gamma is equal to 1 plus alpha. So we subtract 5 from the alpha term. That's good. And then 5 from the constant term. Not quite. And so we're off by 3, and then, which means that 4 gamma squared minus 5 gamma plus 3 is equal to 4 alpha squared plus 3 alpha plus 2, which is in fact gamma cubed. So does that make sense what I just did there? Are there any questions about what I just did there? Let me finish this, and then I'll ask that in a slightly different way. So what we get is that gamma cubed minus 4 gamma squared minus 5 gamma plus 3 is equal to 0. And then and yeah, that's the name of that tune. And so that's going to be our irreducible polynomial. Let's see. So I guess yeah, there it is. I mean, I guess just to be sure, just to double check, we should. Well, I mean, so this is irreducible because it's definitely going to be irreducible because it's the lowest possible degree. But just to sort of double check, to confirm that we got that we didn't sort of do something totally crazy. This is going to be. Oh, hi.
Question. Is it supposed to be plus 5 gamma minus 3? Or is that supposed to be in parentheses?
Yes. Fail. Thanks, everybody. I just failed Math 18A. Thank you. So as I was saying before, I was so rudely interrupted. Thank you, Purva. Yeah, this that's gamma cubed minus 4 gamma squared plus 5 gamma minus 3 is equal to 0. Thank you, Purva. And this is irreducible because there's no, for example, there are no roots in F2. As well as the fact it's also irreducible because it's the lowest degree polynomial that gives you, it's the lowest degree polynomial that gives you a linear dependence among the powers of gamma. And yet I feel like so should I read? Would anybody like to see me redo that as a sort of a formal linear algebra problem where I like write it out with like I could start it with like matrices and stuff? Or should we move on? Go ahead and type on it. No, this is actually just the same. I'm just gonna let me just for kicks, sort of just do that one more time as a formal problem in linear algebra. So as a more formal linear algebra problem, you set this up as follows. You would want to say I think you'd still want to phrase this as gamma cubed is equal to a linear combination of gamma squared and gamma and 1, and then solve for A, B, and C. And then we'd see on the one side that gamma cubed, we just saw was, let's see, 4, 3, 2. Gamma cubed was 4 alpha squared plus 3 alpha plus 2. Yep. And gamma squared is alpha squared plus 2 alpha plus 1, and gamma was alpha plus 1, and 1 is 1. Okay, and then once you do that, you could just and you could then compare coefficients on both sides and solve and do linear algebra. So if you thought that the way I did that sort of came a little bit out of nowhere, then you can really just boil this down to a standard problem by writing it out like this, and you compare coefficients on both sides and do sort of standard linear algebra. So there is, you don't have to sort of try to do it off the top of your head like I did, especially since I did it wrong. Though I guess I would have made the same error over here. But it is really a sort of straight ahead linear algebra problem. Anyway, so everybody good with that? Everybody good with finding the irreducible polynomial? Oh, Robbie has a question. How do we notice that? Robbie asks, how do we know that to set gamma? Oh yeah, cubed is equal to. How do we know to set this in the first place? Oh, that's an excellent question. Yes. So Robbie asks, why do we know that this is going to work anyway? And the reason is, so let me do a little arrow here. Okay. So why? So Robbie's asking, why is it that we knew this is going to be possible in the first place? This is from so Q of alpha has dimension 3 over Q, and in fact, we know that alpha squared, alpha, and 1. Oh, actually, so let me put this. So Q of alpha has dimension 3 over Q. We know that 1 and gamma squared, we know that's linearly independent. Because, well, for one thing, because each degree of alpha shows up only for the first time in each new power of gamma. And so because we know, because one alpha squared is linearly independent, that implies that one gamma squared is independent. So we know that that's linearly independent and is therefore a basis for Q of alpha over Q. So any vector and any element of Q of alpha is a linear combination of 1 gamma and gamma squared. So that, which means that this has to have a solution. Does that make sense? Yeah, so that, I mean, you could also, I think the same argument that allowed me to do this calculationally also shows that any elements, any linear combinations of 1 alpha and alpha squared is a linear combination of gamma squared, gamma, and 1. You can keep doing the same reduction thing, but it's also useful to know that abstractly, and that's why. By linear algebra. Linear algebra is great stuff. Like I said, I never really appreciated it until I started teaching it. But it's good stuff, man. Okay. Good so far? Any other questions? Okay. All right. So now I want to talk. So this is, I mean, I guess it occurs to me right now, maybe you just sort of right now. I mean, we skipped ruler and compass. I guess I should let me note that, just in case. I mean, that stuff is really fun, but it's not strictly necessary for what happens later. And so skipped ruler and I can't spell today, and compass stuff. And let me check. That's the correct section of the book. Yeah. 15.5, because it's not strictly necessary for what happens later. It is really fun if you want to read it, but I think it is also sort of something that because it's kind of fun. It's if you did field theory in 128b, that's something you're likely to have seen, maybe even remember. Okay, so we're just going to go ahead to. So unfortunately, that means that our chapter 15 is going to be a little bit kind of technical. There's a lot of technical stuff in it, and kind of less fun. But okay, don't you know, we're actually we're getting to something pretty cool pretty soon in 15.7 when we develop finite fields. All right, so joining roots. So what we're going to talk about for the last half of today is we're going to talk about various technical constructions in adjoining roots. Let's see. So we're going to talk about sort of how to adjoin a root in general. We'll review that. We'll talk about the idea of a splitting field. Oops. Let's see. There we go. Idea of a splitting field. We'll talk about divisor. What happens to divisors when a divisibility properties when you extend the field of coefficients of a ring of polynomials. Yada yada. Oh, and then this is kind of it's kind of a little bit silly but kind of fun. We're going to talk about the derivative of all things, and we'll talk about multiple roots. Sort of how you use derivative in multiple roots, and and especially the multiple roots of an irreducible polynomial. So that at least is it's sort of not terribly deep in many ways, but it's super fun. It's just sort of weird that you can do the derivative, that you can define the derivative over an arbitrary field. I remember thinking this when I first time I saw that. I thought that was very cool. Okay, so again. So there we go. Yeah, adjoining roots, splitting fields, and multiple roots in the derivative. So here goes. That's kind of a, so 15.6 is like a little bit of a grab bag of kind of technical things. This is meant to be reviewed, so let me remind you. So recall that if you take f bracket x and mod out by a single polynomial f, little f, then you get a field exactly when f is irreducible. So given an irreducible f is what I want to say here. Given an irreducible f, little f and big F of x, you can abstractly construct a finite extension of capital F containing a root of little f, which is exactly f is irreducible. If little f is irreducible in big F, you exactly mod out by f, and then you get a field extension. And the idea, and remember that the degree of k over f will now be the degree of little f. So that creates an extension field of capital F, and the image of little x in capital K is a root of f in capital K. So we often we've done this a couple times. I think we actually just did this, and so we'll often think about we'll often just notationally use alpha or beta and so on in place of x bar. Yeah, so that's a very so example. For example, when you look at our previous example where we're finding the irreducible polynomial sum of some element gamma. Well, what we're doing, or what's happening over here is this field K is Q adjoining a root of. Actually, let me repeat that. So for example, so to construct Q of alpha, Q adjoin alpha, where alpha cubed minus alpha squared minus 1 equals 0. Is constructed as Q adjoin x mod the irreducible polynomial x cubed minus x minus 1. And we say that Q adjoin alpha is Q adjoin a root of x cubed minus x minus 1. So I just introducing a little terminology here, just in case because it's helpful, and I might actually sort of use this terminology without realizing it. So just so you know what I'm saying when I say that. Oh yeah. So the point is that if you want to adjoin a root of a given irreducible polynomial, you constructed it by making a ring of polynomials and killing the irreducible polynomial. So I hope that's review, or you might want to, if it doesn't sound familiar, you might want to go back and look at this. In any case, are there any questions about this at the moment? Those of you who watch this stuff on YouTube, how awkward are these like 10-second pauses? Are they like a little bit awkward, super awkward? You just fast forward through them. You could do, I'll make sure to make them all 10 seconds so you can hit the 10-second skip button. Oh, what was the text above the theorem? Thank you, Rupa. So this is saying that recall that when you take a ring of polynomials over F and you kill an irreducible, and you kill a polynomial, that's a field exactly when little f is irreducible. And so so conversely, if you start off with some irreducible, we can just abstractly construct a finite extension of big F containing a root of little f. And this is, so how do I construct an extension of Q that has a root of x cubed minus x minus 1? Well, I do exactly this. Yeah. Thanks for asking, Apurva. Okay, any other questions at the moment? Let's see. I tried this earlier and had, this is the thing that, oh my God, this is the thing that didn't work. Escape. Whew. All right. That was weird. Escape finally worked this time, but yes. All right. Okay, so now that I know that works. Okay, so let me give everybody, especially if you're watching along at home on YouTube, let me give you just a little. There's a freeze frame of the entire slide, and you can look at that later if you want. All right. So now we're back to this view. Okay, so let's talk about splitting fields, and this is mainly introducing the term. Or the term splitting. Splitting field we'll see later. So to say that little f in big F of x splits in k means that f of x factors into linear factors over k. So to split a polynomial entirely means that that you factor into linear factors, that you sort of i.e. k i.e. So we make this box a little bigger. No. K contains all roots of F. Something which sort of doesn't mean anything, because, well, what I mean by all roots of F, I mean F has no roots. If F is irreducible, then F has no roots in K. But it's helpful to think of it that way, that you've enlarged K this by adding sort of all possible roots. Yeah. So theorem to say that F is a field, and little f and big F of x is monic over degree over 0. So there exists a big K over F such that an extension big K of F, big F, such that F splits over big K. Well, one way to do this is to adjoin roots of F until F splits, and which holds by induction on the degree of F. You know what? It suddenly occurs to me that this is kind of an empty statement. So let me do an example. Let's take f equals the rationals, and little f of x equals x cubed minus 1. So I want to construct actually, let me make it x cubed minus 2. Construct a field extension of Q in which F splits. So okay, so first of all, so somebody want to, actually, let's try this. So somebody want to tell me in the chat box, what's one root of F? Q root of 2, very good. Thank you, Trent. And so we can take F1. Let me start that. Let's say F1 the first time. Let's take Q, and we're going to join the cube root of 2. Oops. So then if we then factor f of x over in f1, what we get is x minus the cube root of 2. So that's our, oh, who picked this example? Terrible. Right. Right. So, and now what you get here, it's sort of not obvious, but what you get is you get x squared plus 2 to the 1/3 x plus 2 to the 2/3. I think that's right. Yes. That 1/3 doesn't look so good, so let me try that again. Wow. So yeah, so this might be a little mysterious as to where I came up with this x squared plus 2 to the 1/3 x plus 2 to the 2/3. But I hope you agree that once I say it, that actually is a factorization of x cubed minus 2. So everybody okay with that first step where we factored little f? Yeah. Okay is probably see. This is because let me type that out just as something. Well, that's like an obscure. That would be like an obscure part of your algebra textbooks. That's because x cubed minus y cubed is equal to x minus y times x squared plus xy plus y squared. And now I guess I should add a new page here. All right, so the problem is here, but f is not yet split, so we need more stuff. And what's not obvious, which is true, something that's true here but not obvious, is that one good thing to add here. So one way to split that last factor is that if we add omega equals e to the 2 pi I over, oops, I better write that bigger, more carefully. Oops, did that too recklessly. No, dang it. So we need to add more. And so omega equals e to the 2 pi I over 3. Yeah, so what is this thing that I just added here? If you draw the unit circle here, it's a reasonable unit circle, then omega is this point over here, sort of 1/3 of the way around the unit circle. And the whole point, and the point of this is that omega cubed is equal to 1. So this is a cube root of unity. And it turns out that these roots of unity are both a sort of very useful thing in Galois theory and factoring, and also a fun example that you can solve completely. All right, so but the point is, it is certainly not obvious. So but it is true that if we let f1 be f2. If you let f2 be f1 adjoin omega, which is f adjoin the cube root of 2 and omega. So it's f adjoin 2 elements. So if we do that, then we can actually split f, little f. F is so we still have that x minus the cube root of 2, but then we also have x minus omega times the cube root of 2, and omega x minus omega squared times the cube root of 2. You know what? I guess this is kind of the reverse of, so earlier, these are the factors corresponding to factors coming from the 3 roots. So I guess, yeah, how is it that I actually remember to do this? So one nice thing about cube roots is that whenever you have a cube root, there's or an nth root in general, there's always, you can always find n possible roots of it by taking the one you thought of first and then multiplying by one of these roots of unity. Those roots of unity, when you take their nth powers, become 1, and so that's how you get that's how you get all possible roots of a polynomial of the form x to the n minus d. And so if you multiply, so I guess I just sort of knew that, but if you want to go, once you sort of know that, you can sort of go ahead and check me that that if you multiply these things out, you can check the factorization. Oops, I can't believe I spelled check wrong. You can check the factorization by using the fact that 1 plus omega plus, so this is a very important thing, plus omega squared equals 0. And so one sort of useful way, one good way of thinking about this geometrically is that if you look at 1 and omega squared on the unit circle in the complex plane, well, their center of gravity is 0, so their average value is 0, which means that their average value is 0, which means that their sum is 0. So there's a sort of it's like a physics proof that that 1 plus omega squared equals 0, or you can sort of you can actually prove that algebraically. Anyway, this is so. Later on, we'll look at cyclotomics, something called cyclotomic fields, and this is sort of what that's about. Later, cyclotomic fields. Anyway, so that having been said, that I was just sort of the point is that the point for now is that f splits not over f1 but over f2, splits over f2 but not over f1. Okay, so that so that's one example of how to construct a field in which and that's actually a very useful example of how to construct a field in which a given polynomial splits. So are there any questions? Let me try this. So are there any questions for now about as to what is meant by for polynomial split over in a field, and sort of questions about how I constructed that? This is where we started. And here's where we ended up. We ended up in order to split that polynomial f, we had to add both the cube root of 2 and omega. Okay. So yeah, so let's talk about how what happens to divisibility in polynomial rings when you extend the field of coefficients. Okay, and most of this is sort of not so interesting. I think I might just do one of these things. So the facts are that suppose you have little f and little g are polynomials with coefficients in the base field capital F, and little f is non-zero just because we're going to divide little g by f, and let k be an extension of f. And let's see. And so the relevant facts are: one, division of g by f gives the same answer whether you're in capital F of x or capital K of x. And two, the GCD of those two polynomials is the same in both capital F of x and capital K of x. Three, if little f and little g have common root in k, they cannot be relatively prime in capital F of x. And conversely, if f and g are not relatively prime in capital F of x, there exists an extension of f, I should say. Oops. Of capital F, in which they have a common root. And finally, if little f is irreducible in big F of x, and little f and g have a common root in capital K, then f actually divides g in capital F of x. I might as well step through this. Why not? So let me talk about the proofs of these just real quick. So let me just sketch these proofs. So one is true because, for example, because long division, if you actually sit there and do the long division of g by f, which you can imagine doing, of g by f only ever involves, if you just go through and look at the process, that only ever involves elements of capital F in the process, right? You only ever divide you only have to ever invert or sort of multiply f by elements of so what's going on by elements of capital F, because all the coefficients of f and g. Oh, actually, I know a better proof of this. Sorry. Let me give you a better proof of this. My bad. Yeah, I was thinking like what's the sort of undergrad sort of sort of applied algebra proof of this. So let me give you the abstract proof of this. If g equals q of x, f of x plus r of x. Well, we know. Let me say that we know that g of x has some quotient of this form in f of x. So and the same quotient in k bracket x is unique. Yeah, because of the uniqueness of division with remainder, the answer that you got in f of x also must be the same answer in k of x. And but still for 2, I'm going to give you the non-abstract version. The non-abstract version is that the GCD of f and g is computed using the Euclidean algorithm, which is really just repeated division. So this holds by. So fact number 2 holds by 1. The hardest thing for me to learn here. So this holds by 1. The hardest for me to learn here is like to grab that little side of that box and make it bigger. Okay, so 3. So if f and g have a common root, then the GCD of f and g is not 1 in k bracket x, so it's not 1 in f bracket x. Conversely, if f and g are not relatively prime in f bracket x, that is if the GCD of f and g is equal to d of x, you can extend, which is not 1, then we can extend f by a root of d. So there's your extension of we saw before. You can always extend by a root of an irreducible a root of an irreducible factor of d. You can always extend a field by to add a root of an irreducible factor. And all right, and the fourth part, part 4 says that if f is irreducible and f and g so if f is irreducible and f and g have common root, then the GCD of f and g is not 1, but since f is irreducible, it must be that the GCD of f and g is equal to f. Well, anyway, so there's a quick rundown of why those 4 things are true, but just for later, it'll be important for to know those facts mostly. Okay, any questions about these? So yeah, don't worry too much about these proofs. The important things are the facts. So are there any questions about these facts? Yeah. So what's important about this? Yeah, I think the important thing to know about this is really, it's going to be this part here. And I guess just this idea of finding. I mean, it all kind of comes from the fact that you have the same GCD, whether it's an capital F bracket x or K bracket x, capital K bracket x. Anyway, any questions about this for the moment? Before I think we'll start the derivative, and then we'll do the multiple roots next time. Okay, so let's do the formal derivative of a polynomial, which is actually, I think it's just I don't know if it's the coolest thing, but it's super fun. So so the fact is, if f of x is a polynomial, and the strange thing about this is that f is an arbitrary field, e.g. F is equal to z mod p. So, I mean, the really weird example of this that you want to think about is like, well, suppose we have a polynomial with coefficients mod p. Excuse me. And the idea is that we can define f prime, the derivative. Can we define the derivative of f? And without any reference to like limits, or I mean, you just do the thing. We just define the derivative of f in terms of the way you would calculate it in calculus 1. Like, well, you bring the. Did I do this correctly? I hope. You bring the coefficient, the exponent down. You subtract 1 from it. Yeah, there we go. Derivative of x squared is 2x. Great. So you can just define the derivative of little f in this purely formal way, and the remarkable thing about this is that the product rule still works. And this is homework. Maybe I haven't decided yet. Maybe this is homework to be done but not turned in. To be done, but maybe not turned in. I think, yeah, I haven't decided what to do for problems at 8 yet, but I think you know, it is just kind of cool that works. Okay, so multiple roots in the derivative. Well, okay, so let alpha be, and the sort of cool thing that happens is that if alpha is in an extension of capital F and little f is, oh sorry, this is not the cool thing. This is what we're trying to study. Suppose alpha is an element of an extension of f, of capital F, and little f is a polynomial with coefficients in big F. To say that little alpha is a multiple root of little f means that x minus alpha squared divides f of x. It's sort of what you would use for way you would refer to multiple roots in regular algebra, in non-abstract algebra. It's just, it means that the corresponding linear factor divides twice. And so the theorem says that in this situation, alpha is a the way to detect that alpha is a multiple root of little f is that to be a root of f means that f of alpha equals 0, but to be a multiple root is saying that f prime of alpha equals 0. Oh yeah, and so corollary, that's right. So this is one. Right, so if f is irreducible and f and g have common root in capital K, then f divides g in capital F of x. So the oh yeah, and this is sort of right, and so this actually so f and g are not relatively prime. There exists an extension in which they have a common root, and if they have a common root, they are not relatively prime. And so yeah, so there exists, so little f has multiple roots in some extension exactly when the GCD of it and its derivative is not equal to 1, is greater than 1, has degree greater than 0. All right, so proof of the theorem. Well, oh, I can't resist. If alpha is a root, then f of alpha equals 0. Well, alpha is a root, I should say. So the first we know that alpha is a root if and only if f of alpha equals 0. That's the root theorem. Root theorem. So in that case, then let f of x equals x minus alpha times g of x. So suppose alpha is a single root, at least a single root of f, and so that means that we can factor this way. So in that case, f prime of x is equal to, now we're going to apply the product rule. It's the derivative of the first times the second plus the first times the derivative of the second. Yes, the product rule. Crazy, huh? Wacky. Product rule. Which means that that f prime of alpha is equal to, well, if I plug in alpha on both sides, g of alpha. So alpha is a root, which means alpha is a multiple root of f if and only if alpha is a root of g, which is true if and only if f prime of alpha equals 0. Cool, no? Product rule. The fact that the product rule works for arbitrary fields is just the wackiest thing. I don't know. Maybe it means that, I don't know. Maybe it means there's something going on there. They're actually studying something instead of nothing. Yes, but that's all because of the product rule. Okay. Anyway, so yes, so right, so we can detect multiple roots by having the exactly when the GCD of f and f prime is when f and f prime are not relatively prime. Okay. All right. So we I guess the first thing we'll do next time is we'll talk about how to use that fact to analyze when an irreducible has multiple roots, mainly for this. So the main application of this is going to be that if in characteristic 0 for us is that in characteristic 0, and say when you start your base field as rationals, then your irreducibles never have multiple roots, and that's the thing that we use all the time in Galois theory. If you have a characteristic, if you have a polynomial characteristic P, then you might have to worry about getting multiple roots of irreducibles, but that won't happen for us. Okay. Thank you for your patience and letting me go 2 minutes over. Stay safe, shelter in place, stay home. It's crazy out there, man. So thanks very much for stopping by, and I'll see you on. I'll talk to you. I'll try to send you a sample exam, which I keep forgetting to do between now and Wednesday, and I will talk to you on Wednesday. Bye.
Thank you. Bye.
Thank you. Bye.
Bye.
Bye.